3. Environmental. Environmental geology. Module 1. Geological timescale and geologic processes objectives. 1. Geological timescale. 1.1 Why do we need a geological timescale and how the geological timescale evolved? 1.2 Understanding the modern geological timescale and the basis of its divisions. 2. Geological processes. 2.1 Geological processes and their role in understanding Earth. 2.2 Concept of geological processes vis-a-vis geological timescale. 2.3 Internal and external geological processes. Who knows for certain? Who shall here declare it? Whence was it born? Whence came creation? The gods are later than this world's formation. Who then can know the origins of the world? The Rig Veda, X 129. 1. Geological timescale. 1.1 Why do we need a geological timescale and how the geological timescale evolved? Introduction. Our planet Earth, the only known habitable planet in the known universe, continues to be a dynamic system. Just as we write and the reader reads, the internal and external physical, biological and chemical processes are continuously reshaping the Earth. Geological processes in general are very slow that we can hardly notice during our lifespan, while some are abrupt and catastrophic. What we observe today on the surface of the Earth is a snapshot resulting from complex. 4. Environmental. Environmental geology. Interplay of many internal processes, and by understanding these processes, the geologists have extrapolated the information to reveal the story of the Earth from its inception. Earth is a jigsaw. How do we understand the story of the Earth? How do we fit these small pieces of this complex jigsaw puzzle to spatially and temporally validate our understanding of the processes today? The reader may appreciate that even to tell the story of the world for the last 100 years, historians would often refer to the global events such as pre-World War I, or post-World War II, or first oil crisis or second oil crisis. Some others may be familiar with the Facebook timeline where a person is choosing to tell her story in a reverse chronological way. Similarly, to tell the story of the Earth, geologists look for global events that can have significant relevance and presence across the planet. Early work on geological timescale. The initial studies that contributed to the understanding of the geological processes were limited in scope to a region or a field. To correlate and construct the story of the Earth has been a very formidable and complex task. It may be important to mention that from the time when interest in this subject appeared, the age of the Earth was not known and information on natural processes was limited to unverified hypotheses. The early efforts to construct this story started in 1600s. One of the earliest attempts to calculate the age of the Earth was 6,000 years by Archbishop James Ussher, mentioned in Genesis, Annals of the World, AD 1658. Nicolaus Steno, a 17th-century Danish scientist, pioneered the field of stratigraphy, study of strata. Contemporary geoscientists to date rely on the timeless principles viz. The principle of original horizontality and the principle of superposition, proposed by Steno to comprehend sedimentary rocks. William Smith, British surveyor, developed the concept of faunal succession. Smith's principle of faunal succession on the basis of characteristic fossils in different strata helps in identifying strata of the same age in different outcrops at different locations. 5. Environmental. Environmental geology. Nicolaus Steno in 1667 found shark tooth while studying the sedimentary strata in Tuscany, what were then called tongue stones, figure 1.1. The concept promoted by Nicolaus that these were remains of sharks left in the rock was not accepted at that time. William Smith worked on understanding the distinct rock types with distinct fossils, that helped him create a sequence that he was able to validate in other parts of England as well. This stratigraphic sequencing was one of the earliest attempts at creating a geological order for assigning relative ages to the rock formations. Figure 1.1 Shark tooth drawings made by Nicolaus Steno. Source, Wikipedia. Charles Darwin's assumptions on age of the Earth was 6,000 years, a common belief during that time. However, based on some geology and his own work on natural selection, he thought that the age of Earth could be several hundred million years, which was not what Lord Kelvin believed. Lord Kelvin's work based on thermodynamics and Earth's thermal gradient predicted a much younger age. 6. Environmental. Environmental geology. There were multiple geological evidence pouring in to support a backward revision in the age of the Earth. At this stage, a better understanding on deposition of sedimentary rocks was developed. While observing the then rate of deposition, estimates on time it may have taken to deposit a thick rock succession was made. As an example, the age of thickest sedimentary sequence such as Grand Canyon was placed at 100 Ma, which supported the theory that Earth is much older than the other estimates that were being made. To simplify our understanding of the story of the Earth, geologists made attempts at the widest divisions of rock strata into eons, periods and epochs. One of the big events that kept shifting the boundary of these divisions was the presence and absence of life, and of simple and complex life. Relative ages. Smith's and Steno's principles were applied to outcrops across the globe in the 19th century. Similar fossils from formations in different parts of the world were found. Fossil assemblages also matched up for these formations along with other cross-cutting relationships. At the end of the century, the geologists could put a time scale together which was the first geologic time scale based on relative ages. Absolute age. The story of absolute ages started when the radiometric dating began. Rutherford in 1905 deduced that radioactivity could be used to give an accurate and absolute age for a rock. This started the trend of isotopic dating that could provide absolute ages. However, till about 1953, the age of the Earth was nowhere close to what we know now. Claire Patterson, American geochemist, calculated age of the Earth to be 4.55 billion years in the year 1956, and this age of Earth calculated on the basis of geochronology has remained largely unchanged since then. 7. Environmental geology. 1.2. Understanding the modern geological timescale and the basis of its subdivisions. Modern geological timescale is a result of many centuries of work put together by geologists that includes understanding stratigraphic successions in the field and studying correlations to comprehend relative ages, and determining absolute ages using radiometric dating. Intervals of geologic time. What is fundamental to the primary divisions of the geological timescale is the presence or absence of fossils and/or distinct set of fossils. The end of a division and start of another demarcates a distinct presence or absence of a particular set of fossils. Eon is the longest subdivision of the geologic time, and two or more eras form an eon. Period is the basic unit of geologic time in which a typical set of rock unit is made, and is usually named after a locality or the distinguishing characteristics of the rocks reported. Devonian, as an example, is named after a locality in England, and Carboniferous period for coal-bearing sedimentary rocks. However, Paleogene and Neogene are an exception and mean old and new respectively. International Commission on Stratigraphy v 2016-04 Figure 1.2 is an agreed upon and elaborate description of the modern geological time scale, which offers numerical age for each eon, era, period, epoch and stage. This represents no finality as numerical ages are subject to further refinement, etc. Primary divisions of the geological timescale. To understand the geological timescale, one can start with its broadest divisions called eons. There are 4 eons: Hadean, Archean, Proterozoic and Phanerozoic. The geological timescale in its tabular form is presented in a reverse chronological scheme, with the most recent at the top. Hadean 4600 to 4000 Ma is the oldest eon and is at the base, while Phanerozoic the youngest at the top. Hadean, the term Hadean, comes from the Greek god of the underworld. This represents a time with absolutely no record of rocks present. One can say that Hadean eon represents those 600 million years of young Earth about which we have no records available. 8. Environmental geology. Figure 1.2 International Chronostratigraphic Chart. Source: International Commission on Stratigraphy. Archean eon 4000 to 2500 Ma was like a new chapter in Earth's history, as the Earth is thought to have cooled off sufficiently to allow formation of continents during this eon. Readers may note during the earlier versions of geological time scale that Archean was considered as the oldest, Greek meaning beginning. To envision the conditions during Archean is to see the planet as a time of high volcanic activity, and so the surviving rocks of the eon are metamorphic and igneous. The readers must also note that owing to the long time gap between the beginning and end of the period, there must have been considerable variation in the conditions of the Earth at the beginning of the eon and at its end. Archean is now divided into 4 eras: Eo-Archean, Paleo-Archean, Meso-Archean and Neo-Archean. 9. Environmental geology. Eo-Archean 4000 to 3600 Ma is characterized by earliest crust and greenstone belts in certain shield areas. Paleo-Archean is younger than Eo-Archean 3600 Ma to 3200 Ma, where the first evidence of fossils ever, dated at 3500 Ma and called stromatolites, were found in Western Australia. The readers may note that newer scientific discoveries would continue to refine and alter our current understanding of the geological timescale. One such recent discovery of stromatolites from Greenland has taken the stromatolite appearance to 3700 Ma 2016 in the Eo-Archean. Meso-Archean 3600 to 2800 Ma is characterized by banded iron formations, when oxygen levels on the planet were still low. Some of the earliest supercontinents formed during this time. Stromatolites diversified during Meso-Archean. Neo-Archean 2800 Ma to 2500 Ma is when continents started to shape up and continued to fragment and assemble through various supercontinent cycles to acquire present-day configuration. Proterozoic, in Greek, means early life, and the eon extends from 2500 Ma to 541 Ma, subdivided into 3 eras, namely Paleo-Proterozoic 2500 to 1600, Meso-Proterozoic 1600 1000 Ma, and Neo-Proterozoic 1541. Earth's atmosphere changed substantially in the Proterozoic, with increased oxygen levels, referred to as the Great Oxidation Event. Although oxygen did show up in the atmosphere in Archean eon, it is only now for the first time that oxygen buildup happened to a certain degree that was conducive for many life processes to follow. Oxygen was a byproduct of photosynthesis by cyanobacteria. In its initial stages, whatever oxygen was produced was taken by dissolved iron or organic matter. At one point these sinks became saturated when no more oxygen could be taken up, at which point it started getting released into the atmosphere. It is also argued that free oxygen in the atmosphere may have been detrimental to the anaerobic bacteria of that time, so in that sense, while it paved way for oxygen that is so required for life, it may have caused the first mass extinction. The other thing that this oxygen did was convert methane into carbon dioxide, less potent greenhouse gas and water, which started the Huronian glaciation, one of the earliest glaciations events in the history of the Earth that led to snowball Earth. 10. Environmental geology. In this way, banded iron formations and later red beds colored by hematite imply an increase in oxygen levels. The other most significant events in Proterozoic are the formation of the supercontinents and further evolution of life. While stromatolites proliferated, eukaryotes or complex organisms showed up for the first time on the Earth. Precambrian. This term was used for everything before Cambrian, and if everyone is wondering what is the most often used name Precambrian refers to, it can be called a super-eon that represents stuff before Cambrian, and combines Hadean, Archean and Proterozoic. Phanerozoic is the current geologic eon. Phanerozoic in Greek means visible life, and it represents the last 541 ma on the Earth, from the start of the hard-shelled organisms to the dominance of humans. The 541 ma years have the most records in terms of life on the Earth and other expressions of geological processes. Phanerozoic eon is divided into Paleozoic, Mesozoic and Cenozoic eras. Paleozoic started with the appearance of first complex organisms, and it is divided into Cambrian, Ordovician, Silurian, Devonian, Carboniferous and Permian. Cambrian 541 to 485 ma, which symbolizes the explosion of life, is known for proliferation of trilobites. Ordovician 485 T0 440 ma was the time of primitive fishes. Tectonically, Gondwana, the large southern amalgam of continental blocks, was at the South Pole in the Ordovician period. Glaciation in this period led to mass extinctions. Silurian 440 to 415 ma is the age when vascular plants as well as arthropods, fish, both jawed and jawless, became widespread. Devonian 415 ma to 360 ma can be called the age of fish's first tetrapods, trees, seeds and amphibian evolution. At the end of Devonian another mass extinction happened. Carboniferous 360 and 300 ma started with high temperature conditions. Trees created carbon that got buried as coal deposits. On the other hand, amphibians were dominant. Later Carboniferous underwent a period of glaciation. Permian 300 to 250 ma is the time when all continents came. 11. Environmental. Environmental geology. Together and formed Pangaea supercontinent, and the ocean surrounded it is called Panthalassa. Conifers also evolved during this period, and this period ended with mass extinctions. Mesozoic era 252 ma to 66 ma, this is called the age of the dinosaurs and further subdivided into Triassic, Jurassic and Cretaceous periods. Pangaea fragmented during Triassic 250 million to 200 ma, and Tethys Sea opened up. Modern corals and dinosaurs, such as Coleophysis, appeared. There was extinction at the start and end of this period. In the Jurassic 200 ma to 145 ma period, primary vertebrates in sea were fish and marine reptiles and ichthyosaurs, plesiosaurs, pliosaurs, crocodiles and turtles proliferated. In Cretaceous 145 to 66 ma period, first flowering plants evolved and sauropods became extinct along with the ichthyosaurs. Deccan volcanism in India and a large meteorite impact in Chicxulub marked the end of Cretaceous period. Cretaceous, Paleogene boundary, previously known as the KT boundary. Cenozoic era is the age of mammals, and divided into Paleogene, Neogene and Quaternary. Paleogene 66 ma to 23 ma comprises Paleocene, Eocene and Oligocene epochs. India and Asia were in the position of collision. All continents started to drift towards their present position. Australian plate separated from Antarctica during this time. One of the significant events in this time was initiation of Antarctic circumpolar current, which cooled the Earth. There is an exceptionally high temperature period in between, called Paleo-Eocene thermal maxima. This period saw the spread of cetaceans, primates and birds. Neogene 23 ma to 2.58 ma comprises Miocene and Pliocene epochs, and during this period, mammals and birds continued to evolve. The movement of plates resulted in North and South America getting connected at the Isthmus of Panama in the Pliocene epoch. The impact of this was that warm Pacific waters were transferred to Pacific only through the Gulf Stream. This led to global cooling and to several subsequent glaciation episodes. This was also the time when grasses spread, which was significant for the evolution of many grazing herbivores that we see today. This is also the time when first hominids evolved in Africa and moved to Eurasia. 12. Environmental. Environmental geology. Table 1.15 Most significant boundary events in the history of Earth and life. Boundary events: age characteristics, life forms appeared, disappeared. Cretaceous Tertiary mass extinction 65 ma, also called the Cretaceous, Paleogene KT, boundary event. Multiple events are held responsible for this drive towards extinction, that includes volcanic activity, also sea level change, rise of mountains and impact of a huge asteroid at Chicxulub in Mexico. Most charismatic animals of the past, the dinosaurs, disappeared along with ammonites, flowering plants and pterosaurs. Triassic Jurassic mass extinction 200 ma, almost half of all species wiped out. Although called as a boundary event at 200 ma, the extinction started 18 million years before as a result of asteroid impacts and volcanic eruptions. Marine reptiles, large amphibians, corals and cephalopod mollusks were largely wiped out. Did not impact plants so much. Permian Triassic mass extinction 258 ma, the biggest extinction event when 96% of the species died out. Asteroid impact, volcanic eruptions and drop in oxygen levels are some of the possible causes for these extinctions. Marine animals and insects, their only extinction episode, wiped out. Late Devonian mass extinction 359 ma, it impacted 3/4 of all the life on Earth. Sea level changes and asteroid impacts, along with change in type of plants, may have contributed to these extinctions. It impacted coral reefs and life in shallow seas. Ordovician Silurian mass extinction 443 ma, third largest extinction event, spread over 2 episodes. 85% of marine life disappeared owing to cooling that impacted the chemistry of oceans. Trilobites, graptolites and brachiopods reduced. 13. Environmental. Environmental geology. Quaternary 2.58 Ma to the present is the time when there is no major change. Glaciation episodes were periodic in this time period. Many animals such as saber-toothed, woolly mammoths and mastodons became extinct. Quaternary subdivisions are based on biostratigraphy, and the two epochs are Pleistocene 2.58 Ma to 0.0117 Ma, and Holocene that begun at 0.0117 Ma to recent 11,700 years ago or 9700 BC. It has been scientifically established that the Earth was born between 4.6–4.5 billion years ago. The current estimated age of the Earth is based on rocks brought back from the Moon 4.4 Ga, and meteorites 4.6 Ga, that are thought to be good representatives of the primary and undifferentiated chemical systems, unlike the Earth where rocks have been recycled several times. This data suggests that the present chemical composition of the crust must have evolved for more than 4.5 Ga. Oldest dated terrestrial minerals and rocks on the Earth. To date, the detrital zircons from a conglomerate horizon in Jack Hills, Western Australia are the oldest dated terrestrial minerals, 4,363 plus or minus 20 Ma. The 4.03–3.94 Ga granitoids and diorites from the Acosta Gneiss Complex, Slave Craton, Canada is the so far oldest rock. 2. Geological processes. Geological processes form mountains in place of oceans and vice versa, and how Earth scientists unearth the Earth's story. They look at mud and see mountains, in mountains oceans, in oceans mountains to be. They go up to some rock and figure out a story, another rock, another story, and as the stories compile through time they connect and long case histories are constructed and written from interpreted patterns of data and clues. This is detective work on a scale unimaginable to most detectives, with the notable exception of Sherlock Holmes. John McPhee, Annals of the Former World. 14. Environmental geology. 2.1 Geological processes and their role in understanding Earth. Geological features that adorn the Earth's surface, both on continents and oceans, in the present form a result of dynamic geological processes that have been operative inside the Earth since the birth of this unique and the only life-sustaining planet of the solar system, almost since last 4.56 billion years. Geological features and events on the Earth are the outcome of a complex interplay of internal and external processes. The former is driven by the internal heat and the latter by the solar heat and atmosphere. James Hutton, Scottish geologist, gave the concept of principle of uniformitarianism. Principle of uniformitarianism. The geological processes we see in action on Earth today have analogy to the geological processes which operated throughout the geologic past. This important concept is known as the principle of uniformitarianism. Charles Lyell, British geologist, in his book, Principles of Geology, being an attempt to explain the former changes of the Earth's surface, by reference to causes now in operation, gave the famous punch line, "The present is the key to the past." 2.2. Concept of geological processes vis-a-vis geological time scale. The concept of geological time is discussed in detail in the above section as the greatest geologic discovery that has revolutionized the way Earth scientists look at the dynamic Earth in the contemporary times. Pioneering geological field and laboratory observations of scientists such as James Hutton, Charles Lyell, Nicholas Steno, William Smith, Alexander von Humboldt, Alfred Wegener, Claire Patterson to name a few, logically convinced us that the present Earth is an outcome of the past geological processes which operated on multiple time scales since 4.56 billion years. The temporal variation is on a large to small scale, i.e. million of years to few years to a fraction of seconds. These geological processes are still operative and will continue to operate in future as well. Thus the face of Earth is ever changing and evolving vis-a-vis the geological time. 15. Environmental geology. Scale. Geoscientists have built up an understanding of the present Earth and how it has shaped up and evolved through geologic time. Lithosphere. Rigid outermost part of the Earth comprising the crust and upper mantle, resting on the weak and ductile asthenosphere. Plate tectonics. Theory which got acclaim during 1960s on the basis of seafloor spreading. The Earth's surface has been divided into large and small lithospheric plates, figure 2.1. The plates are in motion and their relative motion with respect to each other determines the type of boundary, convergent, divergent or transform. Continental drift. Alfred Wegener, a German meteorologist and explorer, formally proposed the breakup and drifting of continents. His theory was based on his observations of rock types, coastline fit, geological structures and fossils on both the sides of the Atlantic Ocean. In his book entitled, The Origin of Continents and Oceans, he proposed that the land masses of the Earth almost fit together like a jigsaw puzzle, figure 2.2. Figure 2.1. The lithospheric plates of the Earth. Source USGS. 16. Environmental geology. Figure 2.2. Concept of continental drift. Source. Source: USGS. The principle of uniformitarianism does not imply that all geologic phenomena proceed at the same gradual pace, but it gives us clues to understand the basic idea how the Earth has evolved since its inception. Geologic processes can occur in a matter of seconds, volcanic eruptions e.g. Colima volcano, earthquakes e.g. Ring of Fire, time span of human life i.e. few years, movement of plates e.g. rising of Himalaya up to 5 millimeters every year, migration of sand dunes etc. Or take millions of years, plate tectonics, assembly and breaking up of supercontinents e.g. formation of the Himalaya, formation of sedimentary rocks, figure 2.3 and 2.4 to shape the Earth's exterior. Let us consider examples of two geological processes operative on short and long time scales. The example of a short time scale is of drop in altitude of a segment of the Himalaya post-Nepal earthquake, which occurred on the 25th of April 2015. The primary stretch that had its height dropped is a 80-100 kilometers stretch of the Langtang Himal, to the northwest of the capital, Kathmandu, said Richard Briggs, a research geologist with the United States Geological Survey, USGS, quoted in Himalayan Drop After Nepal Quake, published by BBC World Service on the 8th of May 2015 in the Science and Environment section. The example of a geological process on longer time scale is the formation of the Himalaya, figure 2.4. John McPhee has beautifully summarized the formation of Himalaya in place of the Tethys Ocean by movement of plates, a geological process on a large time scale, and how once the marine fossilifers limestone which formed in the Tethys Ocean now constitutes the summit of Mount Everest, box below. 17. Environmental geology. Environmental. Figure 2.3. Formation and breakup of supercontinents during the geological time scale. Source: Precambrian Research Journal. 18. Environmental geology. Environmental. Figure 2.4. Formation of Himalaya. Source: USGS. (19) Environmental geology. Environmental. 20. Environmental. Environmental geology. The Himalayas are the crowning achievement of the Indo-Australian plate. India in the Oligocene crashed head-on into Tibet, hit so hard that it not only folded and buckled the plate boundaries but also plowed into the newly created Tibetan Plateau and drove the Himalayas 5.5 miles into the sky. The mountains are in some trouble. India has not stopped pushing them, and they are still going up. Their height and volume are already so great they are beginning to melt in their own self-generated radioactive heat. When the climbers in 1953 planted their flags on the highest mountain, they set them in snow over the skeletons of creatures that had lived in a warm, clear ocean that India, moving north, blanked out. Possibly as much as 20,000 feet below the seafloor, the skeletal remains had turned into rock. This one fact is a treatise in itself on the movements of the surface of the Earth. If by some fiat, I had to restrict all this writing to one sentence, this is the one I would choose: the summit of Mount Everest is marine limestone. John McPhee, Annals of the Former World. The best way to exemplify John McPhee's quote is to look at the summit of Mt. Everest, the highest peak of the world, which is made up of the Chomolungma Formation, Ordovician limestone, 488 to 443 million years old, in which many marine fossils such as trilobites, crinoids, and ostracods are entombed. Figure 2.5. Figure 2. 5. Rock exposures on the Mt. Everest. Source: Wikipedia. 21. Environmental. Environmental geology. 2.3. Internal and external geological processes. The internal and external geological processes are instrumental in keeping the Earth dynamic and geologically vibrant. These geological processes manifest on the surface in the form of volcanoes, earthquakes, drifting, movement of lithospheric plates, formation of supercontinents and their dispersal, sedimentary rocks, ore deposits, etc. Figure 2.3. To understand these geological processes, geologists track the information concealed in various rocks. There are limitations to the accumulation of this data because of the dynamic nature of the Earth. It is not possible to retrieve all the records preserved in the rocks in the past, and records are obliterated due to weathering and erosion of rocks and subduction of earlier rocks both in oceanic and continental environments. Almost all oceanic crust older than 180 million years has been subducted back into the mantle. To understand the geological story of Earth, it is important to have an understanding of the pace of these processes and their driving mechanisms. Sources of heat for internal processes. There are two principal sources of heat responsible for the internal geological processes. 1. Primordial heat. This heat has been escaping the Earth since its inception, resulting from the collision of the planetesimals and the later accretion and gravitational differentiation, which led to three distinct layers of Earth, viz. Crust, mantle and core. 2. Radioactive elements. The heat generated by decay of radioactive elements contributes significantly to the Earth's internal heat engine. The internal heat is responsible for generation of melts and convection currents in the mantle, which are important in terms of large-scale magmatism and plate motions. Figure 2.6. Geothermal gradient is the variation in temperature with depth, an indicator of the Earth's internal heat. The average geothermal gradient on the continents is 30 C per kilometer. The geothermal gradient is enhanced in active volcanic areas, mid-oceanic ridges, and lower in old cratons and subduction zones. 22. Environmental. Environmental geology. Figure 2.6. Internal heat engine. Source: Wikipedia. Geological features is a result of internal geological process. Internal geological processes like plate convergence, plate divergence and volcanic eruptions tend to lift and modify Earth's relief. The plate convergence collision has resulted in mountain chains. The mighty Himalaya was created when the Indian and the Eurasian continental plates collided some 40 million years ago, figure 2.4. All along the western coast of South America, the plate convergence in the form of collision of oceanic and continental plates resulted in the formation of Andes Mountains. Volcanic eruptions have led to the formation of Deccan Plateau during the Cretaceous period when Indian plate passed over Reunion Plume during its northward journey. The divergence of lithospheric plates in the oceanic environment results in the formation of mammoth network of mid-ocean ridges, example, the Mid-Atlantic Ridge, East Pacific Rise, 90 East Ridge, etc. East Pacific Rise and Mid-Atlantic Ridge are examples of relief on the ocean floors. Large-scale magmatism in form of extensive and regional igneous provinces could be explained by intraplate magmatism in the rift environments. 23. Environmental geology and mantle plume activities, example, the East African Rift System. The convergence of plates, subduction is responsible for opening of back arc basins giving rise to opening of seas, example, the Japan Sea. The internal geological processes significantly build the Earth's relief. Sources of heat for external processes. Solar energy is the most important source of heat for all external geological processes operating on the Earth's surface. It creates variations in temperature and pressure in the atmosphere that generates wind, including the monsoon. These processes also complete the hydrologic cycle wherein the water changes its domain and forms. From the oceans, rivers, lakes and even glaciers it gets evaporated and is reintroduced into the Earth's system through various forms of precipitation such as rain and snow. The activity by rain, wind, snow, glaciers, rivers and oceans promote geological processes on the Earth's surface. Geological features is a result of external geological processes. External geological processes, primarily driven by the solar energy, constantly shape the Earth's surface at variable rates. External agents such as water, ice, wind and also the human beings are responsible for the changing face of the Earth and modify the existing relief. Highlands are eroded by various external geological agents and the eroded materials are transported to lowlands and thus result in infilling of the basins and depressions on Earth's surface leading to the formation of sedimentary rocks. These activities over millions of years led to the formation of landforms such as deep valleys, deltas, sandbars, river terraces, beaches, etc. Different places on the Earth experience disparate rates of external geological processes. The factors which control the formation of landforms are the climate, location, latitude and longitude, rate of weathering, erosion, transportation, deposition, prevalent lithology and relief of a given place. The processes may operate for millions of years before changing landforms. Sedimentary rocks, particularly those enclosing fossils, are important in deciphering relative ages of rocks. These sedimentary rocks also preserve the earliest life records and are very crucial in understanding the Earth's paleo-environments and evolution of diverse life forms. Environmental geology. 2.2 Introduction. Earth scientists in the past have evolved new ideas and theories about the origin of continents and oceans and mountain building processes, drifting of the continents, spreading of the ocean floor, presence of trenches and underwater mountain ridges in the ocean, chain of oceanic island. In this chapter we will be discussing about those ideas and hypotheses that have led to the development of plate tectonics theory. 2.3 Concept of mountain building. Let us learn about the basic concepts, hypothesis and theories of mountain building. Then we would discuss how this led to the development of the theory of plate tectonics. The process of mountain building is also known as orogenesis, which has been derived from two Greek words, oros, meaning mountain, and genesis, meaning origin. Mountains are often called origin in geological studies, which represent a comparatively narrow deformed zone over the globe. Earth, in its geological past, has several times witnessed the process of mountain building. The development of orogenic belt occurred during several impulses called orogenic phases. Orogenic belt consists of one or several related mountain systems which have been deformed in an orogenic period. Each orogenic cycle is characterized by distinct glaciations, volcanic activity and evolution of fauna and flora. Each orogenic cycle is characterized by distinct glaciations, volcanic activity and evolution of fauna and flora. In the history of the Earth, three major orogenic periods, comprised of several orogenic phases, have been recorded. These are Precambrian orogeny, before 550 million years ago, e.g. Rhodinian orogeny at 1100 Ma. Hercynian orogeny, at the end of Paleozoic about 350 million years ago, and Tertiary or Alpine or Himalayan orogeny, Paleocene, i.e. 65 million years ago to present day. 2.4 Theories of mountain building. Now before proceeding further, let us briefly read about the historical perspectives of plate tectonics. The major hypotheses and theories that have been put forward to explain the causes of origin of mountains are 1. Contraction hypothesis. 2. Expansion hypothesis. 3. Continental drift hypothesis. 5. Environmental geology. 4. Oscillation and undation theory. 5. Convection current hypothesis. 6. Theory of plate tectonics. 2.4.1 Contraction hypothesis. The idea of contraction hypothesis given by Origen in 19th century, which was later developed by Jeffreys in 1929, on the basis of the thermal history of the Earth. He proposed that the inner portion of the mantle below 700 kilometers was neither cooling nor changing in volume, and the outermost layer about 100 kilometers had already cooled to reach equilibrium, and this too was not changing in volume. Thus cooling and contraction were confined to the layers at the depth between 100 kilometers and 700 kilometers. This zone was thus in tension, but its contraction and thinning resulted in compression in the outermost layer above 100 kilometers. 2.4.2 Expansion Hypothesis. Carey, on the basis of paleomagnetic and paleoclimatic studies, postulated that oceanic area is expanding and the globe as a whole is also expanding in 1958. Thus he believed that the original diameter of the Earth was less than half of its present size and surface area was less than a quarter. Thus worldwide expansion breaks the Earth's crust into blocks. These blocks tend to rotate sinistrally anti-clockwise in the southern and dextrally clockwise in the northern hemisphere because of shearing forces created between polar and equatorial regions due to adjustment of angular momentum. But the questions which remain to be answered are: has the expansion actually occurred? Has the ocean water remained constant in volume? 2.4.3 Oscillation and undation theory. Harmon in 1930 postulated that the disequilibrium in the layered Earth's crust was created due to the vertical movements, which were generated due to the influence of an undefined cosmic factor. This resulted in the formation of geotumors, separated by geodepressions, caused by the flow of subcrustal ceolic matter from the depressions to the tumors. When the cosmic influence moved in relation to Earth, the tumors also moved. This resulted in oscillation of emergence and submergence. In the second phase, the sediments in depressions were lifted up, and the idea of contraction hypothesis given by Werigen in 19th century, which was later developed by Jeffreys in 1929, on the basis of the thermal history of the Earth. He proposed that the inner portion of the mantle below 700 kilometers was neither cooling nor changing in volume, and the outermost layer about 100 kilometers had already cooled to reach equilibrium, and this too was not changing in volume. Thus cooling and contraction were confined to the layers at the depth between 100 kilometers and 700 kilometers. This zone was thus in tension, but its contraction and thinning resulted in compression in the outermost layer above 100 kilometers. 2.4.2 Expansion Hypothesis. Carey, on the basis of paleomagnetic and paleoclimatic studies, postulated that oceanic area is expanding and the globe as a whole is also expanding in 1958. Thus he believed that the original diameter of the Earth was less than half of its present size and surface area was less than a quarter. Thus worldwide expansion breaks the Earth's crust into blocks. These blocks tend to rotate sinistrally anti-clockwise in the southern and dextrally clockwise in the northern hemisphere because of shearing forces created between polar and equatorial regions due to adjustment of angular momentum. But the questions which remain to be answered are: has the expansion actually occurred? Has the ocean water remained constant in volume? 2.4.3 Oscillation and undation theory. Harmon in 1930 postulated that the disequilibrium in the layered Earth's crust was created due to the vertical movements, which were generated due to the influence of an undefined cosmic factor. This resulted in the formation of geotumors, separated by geodepressions, caused by the flow of subcrustal ceolic matter from the depressions to the tumors. When the cosmic influence moved in relation to Earth, the tumors also moved. This resulted in oscillation of emergence and submergence. In the second phase, the sediments in depressions were lifted up, and consequently glided down the slopes of the new tumors. Later, the folded and structurally accumulated rocks were lifted up, and in the third phase they became mountain chains. The main objection to the theory is that the basis of cosmic influence is not known, and also the gliding tectonic is not able to explain the structural features of all mountains on Earth. 2.4.4 Theory of continental drift. The thinkers, philosophers and scientists had realized that the coastlines on both sides of the Atlantic Ocean were juxtaposed together like a jigsaw fit, figure 8.1 and 8.2, which gave birth to 6. Environmental geology. The theory of continental drift. This theory states that the continents are not stationary. They have moved in the geological past. The concept of continental mobility was initiated by F.B. Taylor, an American physicist, in 1910. However, Alfred Lothar Wegener, 1880-1930, is recognized as the originator and pioneer of the theory of continental drift. Wegener was German meteorologist and geophysicist, first suggested this theory in 1912 and propounded this new idea in his book, Die Entstehung der Kontinent und Ozean, The Origin of Continent and Ocean, which appeared in 4 editions during 1915 to 1928. Figure 1 Jigsaw fit of the coastlines of Atlantic Ocean. Source. Wegener recognized and termed the supercontinent as Pangaea, meaning all lands, and oceanic part as Panthalassa, meaning all oceans. Thereafter Pangaea got fragmented into many smaller continents which drifted across to acquire present-day disposition of the continents. Figure 3. Wegener's theory was based on evidences from geological data, continuity of older structures, stratigraphic formations, fossil fauna and flora across the present continental shorelines. The present-day southern continents were centered on the pole and the northern continents around equator. It was brought to the notice of the world by Wegener that the presence of widespread glaciations in Permicarboniferous times, around 225 million years ago, had affected most of the southern continents while the northern continents had experienced tropical conditions. The continental drift occurred in response to the centripetal force experienced by the continents because of the Earth's rotation. 7. Environmental geology. Figure 2 Present-day coastlines of Atlantic Ocean. The continents are depicted by shades of yellow while oceanic areas by shades of green. You can notice presence of a ridge in the middle part of the ocean. Source. Wegener considered the centripetal forces exerted by Earth's movement as the reason for the drifting of continents. This was the weakness in Wegener's theory, that it could not satisfactorily answer the most fundamental question, like what kind of forces could be strong enough to move such large masses of solid rock over such great distances. Alexander du Toit, in 1937, the professor of geology at Johannesburg University, was Wegener's staunchest supporter. He proposed that Pangaea first broke into two large continental landmasses, Laurasia and Gondwanaland. Laurasia comprised North America, Greenland, Europe and Asia in the northern hemisphere. Gondwana consisted of South America, Antarctica, Africa, Madagascar, India and Australia in the southern hemisphere. Laurasia and Gondwanaland then continued to break apart into various smaller continents that exist today, figure 3. The term, Laurasia, was developed from a combination of Laurentia, a region of Canada, and Asia, while Gondwanaland, meaning land of Gonds, after an ancient tribe in Madhya Pradesh. The two supercontinents Laurasia and Gondwanaland were separated by an ocean named Paleo-Tethys Ocean after the Greek goddess of the sea, Tethys. Evidences of continental drift. There are several evidences in support of the continental drift theory. Let us examine some of these. 1. Geometrical reconstruction. You would find that the continents fit together like zigzag, figure 1, which shows that the continents may have been once united together, which later on. 8. Environmental geology. Fragmented and drifted apart. Wegener noticed the remarkable similarity between the coastlines on opposite sides of Atlantic Ocean, figure 1 and 2. 2. Geological evidences. Geologically, the coastlines of the landmass on both sides of the Atlantic Ocean are found to be identical in terms of lithology and stratigraphy, fossil content, geologic structures and style of tectonic deformation. Madagascar, Falkland, Peninsular India, Australia and Antarctica suggest that they were unified landmasses. 3. Paleoclimatic evidences. The paleoclimatic data supports the idea of mobility of continents. The evidences of glaciations of Carboniferous times are found equally on the South America, Southern Africa. 4. Paleontological evidences. Fossils of land plants like Glossopteris and Gangomopteris are found in rocks 225 million years ago, widespread in the places over Africa, Australia, India, which are now distant apart, suggests all these continents were part of Gondwanaland. 5. Seafloor spreading. The studies of seafloor spreading phenomenon have confirmed that the continents were once united as a supercontinent Pangaea, which later got fragmented and drifted. The seafloor between these drifted continental blocks has spread during last 200 million years. 6. Paleomagnetic evidences. They are based on study of the Earth's magnetic field through the geological time. The underwater range of mountains, which are known as mid-oceanic ridge, more, has been active in geological past and still it is. It pours out lava called basalt rock rich in iron and magnesium minerals under the sea. The crystallization of magnetic minerals like magnetite is affected by magnetic forces. 9. Environmental geology. Figure 3 supercontinent Pangaea later began to break up about 200 million years ago. It eventually got fragmented into the continents as we know them today. Source. More and more such paleomagnetic studies on the Earth have suggested that the magnetic north and south poles have wandered from place to places and even reversed their positions in its history. It has been observed that the magnetic pole positions of the present globe were different during the geologic past, and by joining these poles, a curve is obtained, which is known as polar wandering curve. 10. Environmental geology. Forces responsible for continental drifting. Let us learn about the different ideas about the forces responsible for drifting of the continents. Tidal forces. According to Alfred Wegener, the continents are dominantly formed of lighter material, Cl, comprising of silicon, C, and aluminum, Al, which float over relatively denser rock material, Sima, comprising of silicon, C, and magnesium, Mg. The drifting of the continents, Cl, is attributed to the gravitational pull of the sun and moon or forces which cause tides in the ocean. The concept was rejected because the tidal forces are too small. Holmes' convection current concept. According to Arthur Holmes, in 1928, convection currents were generated due to radioactive heating in the interior of the Earth. The concept could not gain importance because the radioactive heating is too low to cause movements of continents. Both Wegener and Holmes' ideas of forces responsible for drifting continents were rejected, but they laid the foundation from which modern ideas developed. Plate tectonic theory. Although Wegener's theory of continental drift had many evidences in its support, but it could not explain properly the forces responsible for the drifting of the continents. Plate tectonic theory considered the role of convection currents, but not in the same way as Holmes had suggested. We would further discuss in this chapter the theory of plate tectonics, which is able to explain the drifting mechanism of the continents. Before proceeding further, we shall discuss the hypothesis of seafloor spreading, which played a significant role in plate tectonics theory. 2.4.5 Hypothesis of seafloor spreading. In the early 1960s, Princeton geologist Harry Hess proposed the hypothesis of seafloor spreading, in which basaltic magma from the mantle rises to create new ocean floor at mid-ocean ridges. On each side of the ridge, seafloor moves from the ridge towards the deep-sea trenches, where it is subducted and recycled back into the mantle. A test of the hypothesis of seafloor spreading was provided by studies of the Earth's magnetism. According to Hess, the drift between North America and Europe would have been accomplished by the gradual growth of Atlantic Ocean. Hess calculated that South America and Africa had both moved 2,500 kilometers apart during an interval of 250 million years from the mid-Atlantic ridge is at 10 millimeters per year. The growth of the ocean floor requires formation of new crustal material for which it is believed that volcanic activity is continuously going on undersea along the mid-oceanic ridges. More evidences of seafloor spreading. The data generated from Joint Oceanographic Institution's Deep Earth Sampling (JOIDES) project in 1969, Figure 4, the Deep Sea Drilling Project (DSDP), an international phase of ocean drilling (IPOD) project in 1976 provided testing ground for seafloor spreading. Provide the following evidences in favor of seafloor spreading theory. 11. Environmental geology. Figure 4 JOIDES resolution is the deep sea drilling ship of the 1990s, which carries more than 9,000 meters of drill pipe, is capable of precise positioning and deeper drilling. Source. 1. The youngest rocks are observed along more while the older rocks occur in the marginal part of the ocean, towards the continent. 2. The active volcanic islands are associated with the crest of mid-Atlantic ridge. The frequent occurrence of earthquakes and lack of sediments at ridge crests explain seafloor spreading. 3. Direct observations, drilling and dredging have provided evidences for seafloor spreading. No material more than about 180 million years in age had ever been recorded from deep ocean floor. 4. Paleomagnetic survey and magnetic anomalies recorded in the rocks of ocean floor provide an evidence for seafloor spreading. Let us discuss the limitations of Hess's idea of seafloor spreading. But if we consider that sea is expanding and nothing of the continent or ocean is being destroyed or consumed, then Earth's area would have expanded to a great extent. Since the Earth is not increasing in surface area by any significant amounts, there must be some other phenomenon that maintains the constant surface area of the Earth. We will try to find answer for this question later in this unit when we study about plate tectonic theory. Convection currents driving mechanism of seafloor spreading. Arthur Holmes proposed that the chief driving mechanism for the seafloor spreading to be the convection currents generated within the interior of the Earth. According to him, the convection currents rise above in a circulatory. 12. Environmental geology. Motion. The places where two convection currents are moving in opposite directions, the ocean floor above expands and new more lava will emerge and spread over the ocean floor. However, his idea could not get acceptance because heat produced by radioactive minerals are not enough to cause such motion. However, later the idea of convection current helped useful in development of plate tectonic concept. 2.4.6 Plate tectonic theory. Plate tectonics is the theory supported by a wide range of evidence that considers the Earth's crust and upper mantle to be composed of several large, thin, relatively rigid plates that move relative to one another. Slip-on faults that define the plate boundaries commonly results in earthquakes. Several styles of faults bound the plates, including thrust faults along which plate material is subducted or consumed in the mantle, oceanic spreading ridges along which new crustal material is produced, and transform faults that accommodate horizontal strike slip between adjoining plates. We will discuss in detail about plate tectonics concept in separate section. 2.5 Concept of plate tectonics. The plate tectonic theory came into light in 1970s through the combined efforts of many scientists of different countries working together or independently. It is considered a comprehensive theory which is able to explain many complexities of continental drift, volcanism, folding, faulting, orogeny, etc. Plate tectonics theory has revolutionized Earth sciences like deciphering of DNA structure has done to life sciences. It has become panacea to explain diverse phenomenon like earthquakes and the spreading of sea floor in a reasonable manner. Let us discuss some basic assumptions of the theory of plate tectonics. This theory assumes that the globe is made up of rigid masses called plates, consisting of lithosphere which floats and moves along the convection current over the asthenosphere. 3 types of plate movement. The convection currents cause 3 types of plate movements, figure 5 namely. Divergent. Convergent strike slip. 13. Environmental geology. Figure 5 cartoon showing divergent plate movement, convergent plate movement and strike slip movement. Source. The theory postulates that due to convergent motion, 2 continental plates collide, the orogeny occurs and mountain building takes place. 2.5.1 Lithospheric plates. Let us get familiarized with some of the terms used in plate tectonics. Lithosphere is the segment of the Earth which consists of Earth's crust and a part of upper mantle lying above asthenosphere, figure 6. Asthenosphere is the layer of Earth which starts just below the lithosphere at around 100 kilometers depth and may extend up to 350 kilometers. This zone is in semi-viscous state and is also known as low velocity zone, LVZ, because seismic waves acquire a low velocity in this zone. All the lithospheric plates float and move over the asthenosphere, figure 6. Plate is the segment of lithosphere, move horizontally over the asthenosphere, figure 6. Earth is assumed to be of many rigid plates. There are 3 types of plates, figure 7. Oceanic plate comprise entirely of oceanic crust. Continental plate comprise entirely of continental crust. Continent-oceanic plate comprises partially of oceanic and partially of the continental crust. 14. Environmental geology. Figure 6 Internal structure of the Earth showing lithosphere and asthenosphere. Source. Figure 7 3 types of plates, oceanic continental plate, continental continental plate and oceanic oceanic plate. Source. 15. Environmental geology. In the current configuration, there are 7 major plates which exceed 107 square kilometers area, figure 8. They are 1. Eurasian plate. 2. North American plate. 3. South American plate. 4. African plate. 5. Indo-Australian plate. 6. Pacific plate. 7. Antarctica plate. There are 20 minor-sized plates, fewer listed below. Nazca plate, Scotia plate, Philippines plate, Caribbean plate, Cocos plate, Juan de Fuca plate, Iran plate, Chinese plate, Arabian plate, Nubian plate, Somali plate, etc. Nature of lithospheric plates. The lithospheric plates are about 100 kilometers thick, are made up of the crust and the upper part of mantle. The thickness of oceanic plate averages about 60 kilometers, increases as we go away from the spreading ridges. Figure 8. Earth is broken into a dozen or so rigid slabs called tectonic plates that are moving relative to one another. Source: text/slabs.html. 16. Environmental geology. 2.5.2 Plate boundary and plate margin. Plate boundary is the surface trace of the zone of motion between two plates. The two plate margins meet at a common plate boundary. Plate margin is marginal part of a particular plate. 4 types of plate margins or plate boundaries have been identified based on types of interactions. 1. Divergent type, where two plates move away from each other. 2. Convergent type, where two plates move towards each other. 3. Transform fault type, where two plates neither converge nor diverge but slide past each other. 4. Triple junction. It is a place or zone where 3 plates meet. Figure 9. 2.5.3 Basic principles of plate tectonics. Let us discuss some assumptions of theory of plate tectonics. They are: 1. As per the principles of plate tectonics, the plates move apart from a divergent boundary and get converged along a convergent boundary. Thus new crust is generated along the accreting of constructive plate margins and destroyed in mantle along subduction zone. 2. New oceanic crust is continuously generated along the active mid-oceanic ridges and seafloor spreading takes place. 3. Divergent plate boundary represents zone of divergence between two plates because at this boundary the two plates are pulled apart. The gap created between them is filled by continuous upwelling of molten rocks coming from mantle, and new oceanic crust is continuously generated. The divergent boundaries are also known as constructive plate margin because the addition of new crust takes place. 4. The whole phenomenon of accretion occurs at the mid-oceanic ridges. More. Mid-Atlantic ridge is present-day example of this kind of plate boundary. Figure 9. All the mid-oceanic ridges present on the globe if taken together are about 65,000 kilometers long. Figure 10. They are located over such a zone where the two cycles of convection currents from mantle upwell from the asthenosphere and subsequently diverge. Mid-oceanic ridges are characterized by the shallow focused earthquakes. 5. Convergent plate margins are where two plates converge towards each other. The denser plate moves down or subducts below the lighter plate. In this course, the crustal part of the subducting plate enters into the mantle where temperature is high enough to melt it. On reaching mantle, the melted portion is no longer part of the subducting plate, hence it is consumed or destroyed. Convergent boundaries are also called as destructive or consuming plate boundaries. 17. Environmental geology. 6. Subduction is downward motion of one lithospheric plate under another. This phenomenon occurs at subduction zone or Benioff zone. These zones are characterized by deep focus earthquakes. 7. Subduction zones are marked by oceanic trenches. They are large linear depressions formed at the junction of two plates. The trenches are the deepest parts in the ocean. The subducted or consumed crust along the subduction zone melts. Subsequently, due to buoyancy, the molten rock pours out as oceanic volcanoes. These volcanoes generally form shape of an arc known as island arcs. The island arcs are generally found in parallelism with the oceanic trenches. 8. The interior of the Earth is responsible for generation of convection currents. The convection currents circulating in the mantle are formed at the boundary of mantle and outer core, where the temperature is very high. Figure 11. 9. Earth is of constant surface area, however the changes occur at insignificant rates. Figure 9 Map of the Atlantic and Eastern Pacific Basin. Mid-oceanic ridges are marked with white arrows. Source. 18. Environmental geology. Figure 10 Diagram showing divergent margin, convergent margin, transform margin, subducting plate, mid-oceanic ridges, trench, island arcs and convection currents in mantle. FSTA, FEMA, 1988. 10. Conservative margins are the margins where two plates neither converge or destroyed nor diverge or generated but only slide or shear past each other along transform fault. The term, transform, is used only for those large strike-slip faults that displace the mid-oceanic ridges. They are those regions along which the two plates slide past each other without creation or destruction of oceanic crust. Figure 8.13. 2.5.4 Causes of plate motion. Convection current theory. Let us discuss the driving forces of plate motion. The theory of convection current has been given by Holmes in 1930. This theory is based on the heat flow in the mantle. This theory could explain the pattern of distribution of continents and oceans. It could also account for the features of active island arcs, such as Japan, Philippines. According to the plate tectonics concept, the convection currents are generated in a circulatory motion which ascend from deep mantle and come to the upper mantle and move to some distances horizontally and finally descend back to the deep mantle. These convection currents have tremendous power to move or drag the lithospheric plate to some horizontal distance over the 19. Environmental geology. Asthenosphere. At place where such convection currents have their motion in opposite directions, the lithospheric blocks called plates move in opposite directions, for example at mid-oceanic ridges. Figure 11. Figure 11 Convection currents. Source. 2.6 Present-day example evolution of Himalaya. Let us read about the present-day examples of plate tectonics theory. Ever since the formation of Earth, plate tectonics phenomenon has been operating. In this process, the continents of the Earth have been unified and fragmented many times. The latest unification of all the continents was identified by Alfred Wegener, which he called as Pangaea, which existed some 200 to 250 million years ago. The Himalayan mountain range demonstrates the present-day example of plate tectonics. Himalayan mountain range resulted when Eurasian and Indian plates collided head-on. Neither was subducted because the continental rocks are relatively. The collision of India into Asia 50 million years ago caused the Indian and Eurasian plates to crumple up along the collision zone. After the collision, the slow continuous convergence of these two plates over millions of years pushed up the Himalayas and the Tibetan Plateau to their present heights. Figure 12. 20. Environmental geology. Figure 12. The collision between the Indian and Eurasian plates has pushed up the Himalayas and the Tibetan Plateau. Source. 2.7 Summary. Plate tectonics theory has revolutionized earth sciences like deciphering of DNA structure has done to life sciences. It has become panacea to explain diverse phenomena like earthquakes and the spreading of seafloor in a reasonable manner. In this lecture we learned about concepts and theories of mountain building process, theory and evidences of continental drift, forces responsible for continental drifting, hypothesis and evidences of seafloor spreading, convection currents as driving mechanism of seafloor spreading, basic principles of plate tectonics, lithospheric plates, plate boundary and plate margin, causes of plate motion and convection current theory, and present-day example of plate tectonics and evolution of Himalaya. References.